Welcome to our deep dive into one of the most fascinating concepts in astrophysics: wormholes. These hypothetical tunnels through space-time promise shortcuts across unimaginable cosmic distances. Fasten your seatbelts and prepare to warp your mind as we venture into the enigmatic world of wormholes. Imagine the universe as a vast, intricately woven tapestry of space-time. Now, picture folding that tapestry so that two distant points touch. A wormhole is like a cosmic shortcut, a tunnel-like structure connecting these two separate points in space-time. Instead of traversing vast distances, a wormhole offers a potential shortcut through a higher dimension. Think of it like this. If you were an ant crawling on a sheet of paper, the shortest distance between 2 points would be a straight line across the surface. But what if you could fold the paper, bringing those 2 points together? That's essentially what a wormhole proposes to do with space-time. These theoretical tunnels are often depicted as swirling vortexes, but their actual shape and properties remain shrouded in mystery. While general relativity allows for the possibility of wormholes, their existence remains speculative. The formation of a wormhole involves unimaginable forces and exotic ingredients. The theoretical recipe includes exotic matter, Einstein's theory of general relativity, and a lot of energy. Exotic matter is theorized to possess negative mass and negative pressure. Imagine a substance so bizarre that it falls upward when you drop it, defying gravity. According to general relativity, mass and energy warp space-time. Exotic matter, with its negative mass, would theoretically warp space-time in the opposite way, creating a kind of repulsive gravity that could open a wormhole. Picture two extremely dense objects, perhaps black holes or neutron stars, their immense gravity warping space-time around them. If these objects were to approach each other under the right conditions, and if exotic matter were present to stabilize the wormhole's throat, a tunnel-like connection could theoretically form. However, the amount of energy required to warp space-time to such an extreme degree is staggering, far beyond anything we can currently produce. The formation of wormholes remains a topic of intense theoretical debate. The theoretical foundation of wormholes lies within the equations of Einstein's general theory of relativity. This theory describes gravity as the curvature of space-time caused by mass and energy. Einstein's field equations describe how the distribution of matter and energy dictates the geometry of space-time. Within these equations, physicists have discovered solutions that permit the existence of wormholes, often referred to as Einstein-Rosen bridges. These solutions describe hypothetical tunnels connecting two different regions of space-time. However, these solutions are highly idealized and rely on assumptions about the distribution of matter and energy that may not reflect reality. One significant challenge in wormhole theory is the requirement for exotic matter. While some quantum effects hint at the possibility of negative energy densities, the existence of exotic matter in sufficient quantities to stabilize a wormhole remains speculative. Theoretical models suggest that these space-time tunnels might be incredibly fragile, prone to collapsing faster than the speed of light. Despite these hurdles, the theoretical framework of wormholes continues to intrigue physicists. The existence of wormholes remains speculative, a tantalizing possibility that has captured the imagination of scientists and science fiction enthusiasts alike. Despite decades of theoretical exploration and countless hours of research, we have yet to observe any direct evidence of their existence. The challenges in detecting wormholes are numerous and daunting, involving both technological limitations and the vastness of space. Their predicted size is incredibly small, potentially on the order of the Planck length, which is far smaller than anything our most powerful telescopes can resolve. Even if a wormhole were large enough to detect, it might be obscured from our view by other cosmic phenomena. Depending on their orientation and the distribution of matter around them, wormholes could be hidden behind stars, galaxies, or other celestial objects, making them even harder to find. Scientists have proposed several indirect methods for detecting wormholes, including searching for gravitational anomalies or lensing effects that could indicate their presence. Gravitational lensing occurs when the gravity of a massive object bends the path of light from a more distant object, creating distorted or multiple images, a phenomenon that could reveal hidden wormholes. If a wormhole were to exist between us and a distant star, its gravity could theoretically create similar lensing effects, providing a clue to its presence. Another proposed method involves searching for unusual radiation signatures that might emanate from the vicinity of a wormhole, offering another potential way to detect them. While the search for wormholes continues, we must rely on observational evidence and rigorous analysis to guide our understanding, always pushing the boundaries of our knowledge. The question of what awaits us on the other side of a wormhole is one of the most tantalizing in science fiction, sparking the imagination of scientists and dreamers alike. While we haven't observed a wormhole directly, our current understanding of physics allows us to make some educated guesses based on theoretical models and equations. Imagine you're an explorer aboard a spacecraft, approaching the swirling vortex of a wormhole, a gateway to the unknown. As you draw closer, you might experience the strange effects of intense gravity, distorting your perception of time and space in ways that are hard to comprehend. Time could slow down for you relative to observers outside the wormhole, a phenomenon known as time dilation, making seconds feel like hours. If the wormhole is traversable, you might emerge into a completely different region of space-time, perhaps billions of light-years from your starting point, or even in another universe entirely. However, surviving the journey is another matter entirely, fraught with peril and uncertainty. The intense gravitational forces within a wormhole could rip your spacecraft apart, stretching it like spaghetti in a process known as spaghettification, a terrifying prospect. To withstand these extreme conditions, you would need some form of exotic matter shielding or a way to manipulate gravity itself, technologies that are purely speculative at this point. Assuming you survive the passage, the destination and the experience on the other side are purely speculative, filled with endless possibilities. The possibilities are as vast and varied as the universe itself, limited only by our imagination and understanding of the cosmos. Wormholes and black holes are fundamentally different, each governed by unique physics and principles. Understanding their differences is crucial as we navigate the world of extreme gravity and cosmic phenomena. Black holes are cosmic monsters born from the death throes of massive stars, collapsing under their own gravity. When a star exhausts its nuclear fuel, it can collapse under its own gravity, crushing its core into an infinitely dense point called a singularity, a region of infinite density. This singularity is enveloped by an event horizon, a boundary in space-time beyond which nothing, not even light, can escape, making it invisible to the outside observer. Wormholes, on the other hand, are hypothetical tunnels through space-time, connecting two distant points in the universe. Unlike black holes, which trap anything that crosses their event horizon, wormholes, in theory, allow for passage in both directions, acting as a bridge. They are like cosmic shortcuts, potentially bridging vast cosmic distances or even linking different universes, offering a fascinating possibility for interstellar travel. Black holes form from the collapse of massive stars, a process well established by astrophysical observations and supported by substantial evidence. Wormholes require the presence of exotic matter, a hypothetical substance with negative mass and pressure, to prop open their throats and prevent them from collapsing, which remains a significant challenge. Black holes warp space-time in such an extreme way that they create a gravitational well so deep that nothing can escape, not even light. Wormholes theoretically create a tunnel-like structure that connects two different regions, potentially allowing for faster-than-light travel. While black holes are well-established astrophysical objects, with numerous observations confirming their existence, wormholes remain purely theoretical and speculative. We have yet to observe any direct evidence of their existence, and their formation and stability pose significant theoretical challenges, making them a topic of ongoing research and debate. Thank you for joining us on this journey through the enigmatic world of wormholes. These hypothetical tunnels through space-time offer a tantalizing glimpse into the boundless possibilities of our universe. If you enjoyed this video, don't forget to like, subscribe, and hit the bell icon for more fascinating explorations of the universe. Keep looking up, and never stop questioning the cosmos around us.